Hello again. Now, welcome to another Light Blade Learning Lab. And today, apart from drinking coffee, we plan to look in this red book. Now, I don't tell my wife, but this red book contains all my old girlfriend's telephone numbers in code. Now, being serious now, what we're going to tackle today is a very important subject that at last we're coming on to, and that's cutting materials. Cutting parameters are probably some of the most important things that you'll need to know to make your machine work properly. Now, we've touched all the other things like the laser tube, the mirrors, all the individual parts of the machine that you need to look after, because none of those are really anything to do with what you bought the machine for, which is to do some work, be creative. And to be honest, until you get some parameters in your head and understand what they are, you still can't be creative. So today is a very important day. Now, as I mentioned in the previous setting, cutting parameters that are supplied to you at this moment in time are really not worth a great deal. They point you in the right direction, but that's all they do. These are a series of Word documents which I will make available to you through the Thinklaser website. So today we're going to get down to the nitty-gritty of cutting parameters. Now, I say cutting parameters, but we've got a book here with a sheet in it for cutting parameters. We've got another one here for marking or outlining parameters, which basically is cutting but not cutting through. So, you know, you may want to defocus. It depends what you want to do with your line, but basically it's drawing with the laser. So that's another set of parameters that you need to understand if you want to do that. Then we've got dotting mode. Dotting mode. Now, dotting mode has got all sorts of uses. Some people use it for instance, if they're doing leather work, they may decide to align stitching marks along their products. So they will use a dotting, a perforation mode that puts dots at a regular interval around the outside of their product. Now, that's one use for it. And another thing is for putting perforation lines if you want to fold a sheet. But to be honest, the most important part of dotting is in fact you can cut with dotting, and you can cut very difficult materials with dotting. And that's something which is very rarely touched upon. Now we move on to scanning. Now, if you've got, for instance, just ordinary text that you've drawn in RDWorks and you want to scan it to make it thick, filled in, engraved text, then this is what you would use, standard continuous scanning. But there is more than just one type of scanning. There's another process which is bitmaps, pictures. Now, pictures can either be things like a logo, which is a black and white bitmap, one set of parameters. Maybe it's a dithered bitmap, like the sort of pictures that are produced in newspapers, lots of dots. Well, that's another set of parameters that you need to understand. And then we've got a grayscale bitmap. Well, you know, we're getting to a lot of parameter pages here. It's not simple. And that's what I tried to mention to you last time, the fact that, you know, there are very basic guidelines out there, but at the end of the day, you will need to generate your own parameters for your machine. Although there will be guidelines, there will only be one set of real guidelines and recipes for your machine, and they're the ones that you produce. Okay, so you've spent ages creating all this lovely data. And a year, 6 months, 2 years down the road, you decide you need another machine. Either the same or different. Maybe it's going to be an 80 watt machine as opposed to a 60 watt machine. Who knows what you're going to change to? How do these parameters work for you then? You need to be very careful because you'll be putting all this information here in something called percentage power, which is what you see on the display here. That's what this machine works in, percentage powers. It doesn't work in watts. So all the parameters that you've got in here could actually be quite meaningless if you move to another machine. By that I mean to say that 20% power on a 40 watt tube is not the same as 20% power on a 60 or an 80 watt tube. So how do you overcome that problem and make your results meaningful? So when you first get your machine, good advice would be to see about a power meter of some sort so that you can physically measure the power coming out of your tube to generate this calibration graph against percentage power. And then if you get another tube, you can draw the same graph and you can work out what the power differences are then between percentage power on a 60 watt tube and the same percentage power on a 40 watt tube. And you can start to adapt and modify these parameters without going through the whole process again. Over a period of time, we will gradually tackle every one of these subjects and start filling in the parameter sheets. The first one is cutting. Now, the word cutting is in some ways a bit of a misnomer, because you're not really cutting. What you're doing is burning. All organic materials like wood, leather, paper, card, they're all burning materials. The process by which you cut them is burning. Acrylic is a unique material in that it sublimates. You fire heat at it and it evaporates. Now, never lose sight of the fact that your laser beam is not an innocuous beam of light. It's a very powerful beam of fire, just over the thickness of a hair. And it can do a lot of damage, but it is fire, heat, concentrated heat energy. And it will burn and it will char and it will smoke. I'm going to show you the procedure that I use to quickly get to cutting parameters and the optimum cutting parameters. We're not going to spend too much time initially filling in this sheet. What we're trying to do is quickly get to the parameters that we can record in here as being the correct recipe. So where do we start? Well, the first thing we need to do is choose a material. And we're going to start off with something nice and simple. Here I've got a piece of 1/8 3.125 hardboard. It's a high density fibre board. I would recommend that you get yourself a program built into your machine here, which is a 40mm square or a 50mm square, something small and compact like that. So you can draw that in RDWorks and program it up with cutting parameters. It doesn't matter what the parameters are that you put in, because we're going to edit those here on the machine itself. Now, to do this cutting, we could use this table. The problem is, people think that you get good extraction through this table, but look, how much extraction am I going to get through here? The answer is very little. The way to get good extraction is actually to let it happen underneath the job like that. So what I'm going to do is to pack that job up. Now, I've mentioned to you before things like these. These are dome nuts. Anything will do for packing up. We'll just put these round the corners of the job so they've got lots of air underneath and lots of air over the top. And then on this 2-inch lens, I need to set the focus to 5mm above the surface. So yeah, I'm nearly at the top there. I'm not going to use autofocus at the moment. There we go. My suggestion is always use the maximum power that you can. I'm going to set the parameters to 67%, which is the maximum I can run on this machine. And then I'm going to set a fairly slow speed. If the square does not drop out, we're going too fast. And if the square does drop out, we're not going fast enough. So we can't lose whichever way we go. We've eventually got to get to the point where the square doesn't drop out. So we'll start off at something like maybe 4mm a second, very slow. The other thing that I want you to note is I have got maximum airflow on here. This air assist is fully open. You don't want any smoke basically coming back up onto this surface. If it comes back, it will get blown down again and it will produce a brown mark around the edge of your cut. So I'll now turn the extraction on. Well, you see, we have some good news. Look how clean the cut is. The second thing is that this dropped out. As I mentioned to you, all organic materials burn, and burning produces smoke and charring on the edge. Now, one of the ways of knowing whether or not you've got a good cut, or you're getting close to the maximum that you can achieve, is to carry out this simple test. Get a piece of white kitchen towel and try rubbing it along the edge. Now, okay, we've got nothing coming off there at the moment, but that may be because this is not a pure wood, this is a man-made wood with resins in it, which will actually harden off. It looks very, very black. Looks quite nice, but it looks black. And I'm not expecting it to be that black. Let's double it. Let's go to 8mm a second. We could go up in single steps and spend ages doing it. But let's double it, because the worst that's going to happen is it doesn't work. And in which case we know that the result, the good result, is somewhere between 4 and 8. So we go through this halving process, doubling and halving, to get to a quick result. Now if we see smoke coming back off the surface there, we shall know that we haven't cut through. I can't see any smoke. We've still got a beautifully clean cut edge. Can you see how this one is black and this one is becoming brown? Now that tells me we're getting towards a good cut. The less charring, the better. I'm pretty confident we're not going to be able to double that again to 16. So I'm going to make a judgment based on the edge that I can see that my next step will be 12. Just make sure we're nowhere near the any of the support points. Okay, I was wrong. Now I'm hoping that you can see there black, brown and even lighter brown. Maybe we could have gone to 16mm a second. Well, I've just picked myself up off the floor. It's important that I keep showing you this. You can see the colour differences between 1, 2, 3 and 4. They're getting lighter and lighter and lighter as we're getting faster and faster, and the burning and charring. We can't go to 32, but we'll add another 4 and we'll go up to 20. Now I suspect, I was just going to say I suspect the beam was dragging a bit there, because if we compare these last two results here, you can see the burning, the browning around the edge that's not there. So we've reached a point where the smoke is beginning to just back up a shade and come out on top. There's our colour comparison. We could push it to 22 and see what happens. No, it's just not falling out. All that's happening is it's hanging right on the corners, because what's happening is the cut, as it travels along, is actually this shape. The beam is dragging, so when it gets to the corner, just here, there's a little bit there which is not quite cut, and then it starts coming towards us. And that's probably these little corners here which are hanging. You can see clearly that we've now got some brown on here. We have reached a limit, but what we'll do, we'll go beyond the limit, 22 to 24. But this time we'll look for some smoke that might be coming off the surface. Again, we could say that this is actually cut. It's done a superb job on the underneath here, and that's another trick that I will point out to you. You don't always cut a product like this face side up. Yeah, and that's just hanging in on the corners again. Okay, now You may think that we've found the limit. I've turned the extraction off so that we can hear what we're talking about. Right, let's just have a quick summary. We've held the power constant at 67%, we've held the airflow constant at full on, and we've kept everything else the same, the distance off the deck and the airflow through the... So everything has been constant, and we've been using speed as our marker of success. So now we're going to change another variable to see whether we can have any major effect. Now, one of the most underrated variables is this thing here, airflow. Another reason why I've turned the extraction off is so that you can hear the airflow coming out of the nozzle. But when I turn it down, is it on? Is it off? Is it working? Is it not working? What's happening? You can hear it when there's lots of airflow, and you can hear it when there's no airflow, but it's that little bit in between, which is actually quite crucial. I'm going to show you a little trick that I found extremely useful. A little pot of water, which I keep handy. I dip the end of my tube in there, so I can make a lot of bubbles. I mean, even with it actually fully turned off, I've still got a small amount of air leakage past there. So that means if I've got air coming out of there, when I plug that back in, the only place for it to escape is out of here. We've got just enough air coming out of there to stop the lens from fogging up, but it's not enough to force the tar-laden air back down onto the surface of the job and make it brown. So now what's going to happen is hot air will come up and the extraction system will take it away before it gets a chance to blow down and recondense on the surface. Now, I know it might seem totally counterintuitive that you turn the air supply off to cut wood. I'm hopefully going to demonstrate that to you now. So we've basically turned the air assist off, but left enough on to protect the lens. We're still doing 24 millimeters a second, which is this last one here. Did you notice anything? Hell of a lot of smoke. It actually cut quite nicely. But the thing that I really want you to look at is this. Smoke, no smoke. Let's look at it again and observe what's actually going on, because part of the process of getting the best parameters is using your eyes. Now, take a look carefully this time at what's happening to the smoke. Can you see how it's blowing up from the surface? And then what's happening is it's getting carried away by the air. Now, I've got the door open at the moment, so what I'll do, I'll close the door, because you would normally be operating this machine with the door closed. And as I mentioned to you in the last session, I've got a big air gap underneath the door, which means I get a very high jet of air that passes through the machine. So can you see how the smoke is actually drifting upwards? I mean, the edge is beautifully clean, don't get me wrong. It's done a superb job with this product. It might not do the same with wood, but with this product it's done a wonderful job without the air assist. Just look at the difference in colour off the edge. Slower, slower, faster, faster, faster. No air assist. But it's a product on its own, this MDF. It's not the same as normal wood because this is man-made wood. We shall just record the results as we go. And when I say no air assist, we talk about just enough to protect the lens. So we think we've got to our maximum speed of 24 millimeters a second. Let's see if we can improve that in any way at all. You may remember that this was set to 5 millimeters. I'm now going to drop this down to 4 millimeters. I did warn you that these fumes are flammable. It has only just about cut. So what we'll do, we'll go the other way and we'll lift the nozzle out a millimetre. We'll set it to 6 millimetres. So lift it up onto the 6 millimetre step. Just tighten it up. Well, we certainly didn't get any flames that time. The product just about falls out still. We've still got quite a nice clean surface finish. So we seem to get the best results when we took the air assist off. Certainly -1 was giving us flaming, and it was only just making it through, but then again it was only just making it through on all of these, so whichever one of these we chose, it was right on the limit of cutting. So we've reached that limit at 24 millimetres a second. We've now got to look to see what other attributes we would like to get out of our cut. The cleanest edge is probably the best thing that we can go for. Now this one here at -1, although we were producing all sorts of flames, we didn't damage the surface. But I think this one here at no air assist, normal 5 millimetre optimum focus, I think the optimum focus 24 millimetre was probably the best one to go for. So we've settled on several things then for this material. 24 millimetres a second, 67% power, no air assist, on standoff. These all look nice and crisp and clean on the surface at the top. This was the first one that we did very, very slowly. And one thing I'd like you to note on this one is how burnt the bottom edge is. Can you see how charred and brown that bottom edge is? Once we started getting a little bit faster, we get lovely clean bottom edges. So there's some other factor that tells you whether or not you're going fast enough or whether you're going too slow, and that's whether you're getting smoking on the bottom edge. Right, now is the time to start filling in some data in our book here. Now it's high density fibre, HDF, 3 millimetres, let's say it's 3.125, but 3 millimetres. Now the important thing is here we were using a 2-inch lens, and so all the data is going to be filled in across this column here. The offset of the focal length, we tried -1 and it flamed up. We tried +1 and it was okay, but optimal was probably 0. So the offset was 0. Minimum power, well, when you're cutting, there are exceptions, but in general, minimum power and maximum power are always set the same. The reason why you'd use minimum power is for cutting is a specialised subject which I will tackle at a later date. So at the moment we had 67% and 67%. I don't know what the workface power is. We'll check that in a minute. We do know what the speed was. The optimal speed that we found was 24 millimetres a second. Now, air assist 0 to 3. We've got a code down here. 0 is off, 1 is just on, 2 is low flow, and 3 is maximum. I would say that we had 1. Because it wasn't turned off, you saw it bubbling. The work support method, if we just put a dimension down, that will tell me that we've just lifted it 12 millimetres off the deck. Now, edge finish, that's interesting here. We call that good. In fact, I would call that very good. It's not charred. So, you know, we've got the opportunity here, if we want, we could put note 1 there, for example, and down here we've got additional notes, and we could put 1. And if you really want to, if you're keeping these in a book, as we might do, you might even stick that on there. Oops, air assist was 1. Table type, what were we using? We were using the honeycomb table. So that was B. Missed 2 things out. Dimensional error. I thought I'd put a 40 by 40 program in there. Hang on, that's not 40 by 40, that's probably 25 by 25, which is another program that I've got loaded in the machine there. So what we need to do is, knowing that this was 25 by 25, just check the 0, yeah, 0, 0. Knowing that this was supposed to be 25 by 25 to start with, it's finished up at 24.88, say 24.9, 24.86. So on average, it's lost 0.15. So the dimensional error minus 0.15. Now that's a very important piece of information, because if you're trying to make pieces that fit together snugly and tightly, you need to know what the error is. Now bear in mind that this is, and I really oughtn't to put, is plus or minus. I oughtn't to put any dimension on that, so it's plus or minus, because if you're producing a shape like this, it's going to be minus, but if you're producing a hole, it's going to be plus. So technically it looks as though that cut width, the kerf, is 0.3. In other words, it leaves a 0.3 gap all the way round. One vital piece of information that's missing off here is what power we were actually using to do that work with. And the only way we can find that out is by measuring the power that comes out of that nozzle with a power meter. Now, here's my little power meter wand that you've seen me using before. It's necessary in this case to have it on a little stand, because you can't use the machine with the lid open. But we can close the lid and we can pull this piece outside. The way that this stand is designed is such that it's got a location pin under here which sits under the centre point of this thing, which I call a doohickey. Now, even if this rotates, it won't really matter, because the centre point will remain the same. They're going to move the head to a position on the centre of this target here. There we go, that's not far out. Because the beam is focused through the lens, if we drop that down to just 5 millimeters, which is the focal point, it will do a nice engraving job on the surface of that black aluminium. Now that's anodized aluminium, which is 100% absorptive to the rays of energy that come out of here, the heat energy. Natural aluminium is reflective, anodized aluminium is 100% absorptive. We've got to drop this down about 2 inches. It really isn't that crucial, provided it's more than a certain distance. And then I'll just put a piece of card on the surface, and we must make sure we turn the air assist off. Otherwise it will cool that surface down, and we don't want that all cooled down, we want to heat it up. So I've got pulse now at 15%, and what I can do, I can just gently pulse that, and we shall see that we've got about a 2.5 millimeter diameter. I'd like to see that at about 3 millimeters. So we'll drop the distance down a little bit further. And we'll do another pulse. That's better. That's more like 3 millimeters. Okay. Now the reason we're doing that is so that the energy density is low enough and that it doesn't damage the surface of that. We're going to move it around anyway. Now although this whole system is basically calorimeter based, it isn't really a true calorimeter because it has to be calibrated against a known standard. Now if you want to understand more about how this system works and how power meters, the cheaper end of the market power meters work, there's a whole session of describing how they work on my RDWorks Learning Lab series. And I can't remember what number it is, but it's somewhere in the middle of probably about 45 or 50. I haven't got a direct watt output. I work against a calibration chart, but the calibration chart is nice and easy to remember. This particular calibration is temperature difference times 2. Just beside the machine here, we have a bucket of water which has been sitting in this workshop for weeks. So it's established a nice temperature, ambient temperature, and we'll just dry it off and we'll put it back in its stand so that it's roughly lined up with the shape that's underneath, just to make it easy for us to line up underneath the nozzle. And as we've got the lid open, I will do everything in one spot so that you can see what's going on. So the number that we need to remember is about 8.4. We'll start the system off to start with. I'll set the maximum now, so 8.4. So I've already put that into my calculator, 8.4. We'll just wait for the set temperature to max out. 29.8. 8.4 minus 29.8 equals, don't worry about the sign, times 2 equals 42.8. So we've got 43 watts coming out of 60 watts in. So that's the important bit. Now that could be the result of the lens rather than the mirrors, that we're getting some losses across the lens. But at the end of the day, 43 watts is the power that we've got to put down into our chart. So our work face power is 43 watts. It's a 60 watt tube. We put that at the top there. And now what we've got to do is exactly the same thing again, but this time we've got to do it for a 1.5 inch lens, and then I should do the same thing for a 2.5 inch lens, and I'll also try and do the same thing for a 4 inch lens. And what you'll then see is the comparative power that it takes to force each one of these lenses through that material. In other words, we may be able to get better than 24 millimeter per second out of a 1.5 inch lens on this thin material. But I suspect when we get up to 2.5, it will drop down. But it really depends on what power is coming through the actual lens itself. So again, I'm just trying to make it clear to you, there are so many variables in here that only you can find out what happens correctly on your machine. So this one's reading 7.1, press max 3.7, 3.6, settles at 28.3. Well, the power meter says 49.2 watts. So this is what I call my everyday power meter, and this one is my Sunday best. This is the one that I use for reference work, just to assure myself that everything's still working okay. just about made it to 50. Just about made it to 50. These 2 meters are reading the same. I'm happy with that. Today's another day. I haven't changed a thing since I did this test yesterday. The temperature's about the same in here. The only difference is that the machine has just been turned on, and yesterday we'd been working the machine for an hour or so, and so today we seem to have 49 watts at the workface. So I don't really know what to believe. So we'll quickly change this lens. That's the 1.5" lens, flat side down. Oops. And this 1.5" lens has got a focal point or focal distance below the nozzle of 6.5 millimeters. Back there, yeah. So we're just filling the details here for the 1.5" lens. We had 0 offset was the best. 67% power, 67% power. The power at the workface, where we checked it earlier, was 49 watts. Speed 24. Air assist, well, we've got full air assist on. So we've got 3. We've got a honeycomb table. The support method again 12 millimeters. Dimensional error, we're not even going to bother to check it because we're not going to take those results as being valid. The edge finish was okay. So we need to fill the data in because we need to know which of these lenses is the best lens, and at the moment we probably have settled on the right one to start with. So we now move on to the 2.5" lens and see what happens there. So the 1.5" lens is a loose system because it's something I've made myself that sits down there inside the nozzle, whereas in fact the 2.5" lens sits right back there. Back in there and just lock it up. Lens changed. We'll put some extraction on and away we go. Now I don't really expect that to cut at 24 millimeters a second. And it hasn't. And we'll give this a try to see whether we can get it to drop out at 20 millimeters a second. Now we knew that it wasn't cutting through, or we could see that it wasn't cutting through because of all the brown stuff on the surface there. And it's not cutting through again because we've got lots of brown stuff on the surface. No. So this is 16 millimeters a second. We're still getting some brown on the surface. But it's just about fallen out, look. Yeah, it has fallen out. Look at the colour difference between that and the 2" lens. So it's certainly not as efficient at cutting. So that's about as fast as we can go. We could try it without air assist, but again, I'm not going to bother with doing the air assist tests because we already know that this is not the right lens for doing this material. So we can fill in what data we have collected and not bother about the rest. Right, so let's fill in the data for that 2.5" lens. Offset 0, power 67, 67, workface power 48, speed, well, we got down to 16. Air assist was on full, B 12. Dimensional error, well, we're not going to be worried about that because we're not saying. The result was okay. and I've put HDF here. I'm going to change that to MDF because I did a little bit of research, and I think this is something called laser grade, and the only reason it's called laser grade MDF is because it has a lower formaldehyde emissions content. How much lower? It's difficult to find out, but basically it's MDF. Now, as I said, I think MDF is going to perform differently to wood. So we're going to go with a little piece of wood next to see what the difference in results are. Now here we've got a piece of 10mm plywood. And we're going to try, first of all, with this 2.5 inch lens. We'll work the other way around this time because we happen to have the 2.5 inch lens in. We're going to start this test off somewhere in the middle. Let's just say 10mm a second. We've got full power on again. We're going to turn the air assist on. We're running at 10mm a second, 67% power. And that looks like it's cutting through very cleanly because we've got no browning on the surface. We'll just check the edge and we'll check it with the tissue, and we appear to have virtually no browning at all on there. Well, let's leave the air assist on at the moment and we'll find out how fast we can run. Let's see if we can get it to run at 14mm, and it hasn't cut through. So 14mm is one step too far. We can see the obvious difference between going low here and even lower here and going high. Here is 0, -1, -2, and this is +1. 0 and +1 look about the same. -1 and -2, first of all, the lines are getting thicker as the beam gets thicker, and secondly, they're also burning more. They're doing a lot more charring. So let's have a look at the back of that +1 and see what that looks like. That's the back of the +1, and again, what we can see is that it hasn't really cut through, more or less. So we're on the edge. We've reached that point where, we accidentally found the perfect settings the very first time we touched it. I've dropped the speed very slightly because we were right on the edge at 10mm. Now, the first thing we note is that as we drop the speed, as we drop the nozzle down, we're getting a little bit more burning on the top surface. But it has dropped out. Maybe just a little bit more charring. So I think we found our ideal setting for 10mm plywood. Now, I don't know what sort of plywood this is. This is a very light grade of plywood. It may be what they call Baltic. It's a sort of wood that's used for packing cases. It's a low, relatively speaking, a low grade, but it's a pretty good grade because there are very few voids in this. One of the standard problems with plywood is you get voids between the plies sometimes where they join the plies together, and it's a matter of what you can't see inside you shouldn't worry about. But for laser cutting it makes a big difference, because if the beam cuts across an air pocket, it will produce smoke which will stop it from cutting right the way through, so you get an intermittent cut. In for our plywood, 10mm thickness, 0 offset for focus, power was 67, workface power was 48 from what we found out with the 2.5 inch lens, 10mm per second speed, air assist was full on, we were on the honeycomb table, work support method was 12mm above the surface, dimensional error, average about 24.8, and this way varying, but about 24.8. So that's 2 millimeters, 0.2, 0.2. Now, we really ought to check to be sure that this dimension in here is actually 25.2, which it is. So, yes, the error is definitely 0.2. And our edge finish, well, I would say that we've got that on good, very good. And it might be a good idea to keep a little box of these samples so that you can always go back and check what edge quality you had. This is the 2.5 inch focal length lens, and this one was a 2 inch focal length lens. So we know the conditions under which we got these ideal cuts. Shows you how flammable the smoke is. It's not produced any charred edge. It's brown, but not burnt. The burning was taking place on the surface here when there was no air assist. Both the top and the bottom of the cut, they're not bad. So with the 2 inch lens, zero focus, 67, 67, 48, we haven't checked, but that was what we found out earlier. Speed 10, air assist 3, table type B, method 12, dimensional error 24.7. So dimensional error 0.3. Question is, should we be stupid and try the 1.5 lens on there? Well, that's a 1.5 inch lens that's nearly cut through at 10 millimeters a second. Now, it's got a very, very short focal length on that lens. So what I'm going to do, I'm going to drop that down by 2 millimeters to 5.5 down to 3.5. 5.5, 4.5, 3.5. There we go. Definitely has had no beneficial effect. So let's try 4.5. So this is 4.5, 10 millimeters a second. Well, this is the cut that took place. That was 10 millimeters a second, and it was at zero focus offset. That was -2 into the material. That was -1 into the material, and that was +1 above the material. So you can see the difference. So we've got the maximum penetration at 0. That means that we can do a cut, but we may well have to drop down to possibly as little as maybe 8 millimeters a second to get the cut to go through. £43.5 watts now. Similar to the results that we had yesterday. Okay, well, we've finished up with our final set of results for Plywood, which was the 1.5 inch lens, which we thought might be a little bit hopeful. It was hopeful, but interesting and revealing. We found that the best results, surprisingly enough, was at 0 offset. Now, all the books and everything will tell you that I should have had that lens probably set 2-3 millimeters into the material. Same with these lenses. It appears not. As I said, we'll always use max power, and we'll decide on the speed that we can get for the maximum power. And here we found that we were able to get the same speed for 2 and 2.5 inch lenses. So which one would you choose? Difficult to say at the moment. With the 1.5 inch focal length lens, we were only able to go at 6 millimeters a second, which was a little bit surprising, but then again it was a thick wood and hard work for it for such a short focal length lens. But the puzzling thing was, as I said, the fact that I had to have the lens set right on the surface to get the best penetration. Now the air assist was right up at the top, maximum, and the interesting thing here was that I was getting some really strange results in terms of the dimensional error. As you can see, the best dimensional error, the tightest dimensions, were actually on the 2.5 inch lens. And the surface was good and the finish was good. So on balance, I suppose for 10 millimeter, I've got to say that I would probably favour the 2.5 inch lens. But I hope you're getting an idea now of the way in which I'm going to be using these charts and the way in which they point you in the right direction. It tells you which lens to use, what speed to use, whether or not you should or you shouldn't use air assist, the surface finish of your product. Everything is built into this chart. You may or may not have this chart on your desk, and so it might not be the most convenient thing in the world for you to carry around once you develop this chart. We can make life a little bit easier for you. So let's go back into the office and we'll take a look at RDWorks. Somewhere on your machine you will find an RDWorks V8, which is the file that contains all the RDWorks information. Even though you load different versions on, what will happen is it'll always find this RDWorks version 8 and overwrite it with the latest version. So if we click on that and we take a look what's in here, you'll find that we've got something here called a parameter manager, and that's as much as you'll find about parameters. So let's close this for a minute, and then we come back here and we'll look at the top of this parameter layer, and we find there's something called a parameter library. Now there's a really weird way to fill in the parameter library. There's a certain amount of logic to it, but you have to get your head around it. So the first thing to do is to decide what parameters you want in here for a particular material. So I've got my big red book in front of me, and we're going to be putting the parameters in to suit 3mm MDF. So we decided that the best speed was 24mm a second. Blowing, yes. Process was cut, yes. We won't worry about anything in advanced. The power, number 1, yes. 67 and 67, fine. We don't want any of this stuff down here. So as far as RDWorks is concerned, we've defined everything. Speed and power. Yes, I think we know a little bit different now. So let's now go to the parameter library. What we want to do is to save these parameters. So we save as, and it will tell me what I want to save it as. Well, the title is, and bear in mind these are likely to be ordered in alphabetical order, so we'll put in MDF 3mm. Let's move this out the way. Let's move this out. Let's move this. So it won't let me do that. So now you've got to remember what might be in this library underneath here, because you can't see it. What I will suggest you do now is to put all the stuff that you can't put into this parameter library into your notes. FL offset equals 0. You can just do a carriage return. No, you damn well can't. So okay, we've saved it as. So we can always get back to this parameter. 3mm MDF. Let's close this now, exit. Let's go back to the file manager. And now we shall find above the parameter manager, we've got something called parameter library, which has appeared. We've started creating a library. Now, if I double click on that, it will say Windows can't open this file. So you can select a program from your list of installed programs to look in this library. Now, depending on what version of Windows you've got, you might be able to look into it with Notepad. It's got to be a fairly advanced version of Windows. I think Notepad might not work. I think you may well have to look in WordPad. Okay, now we're in WordPad. We've got all these things that we can look at. But the thing that's important to us is what's at the top here. Okay, now we can't use a carriage return. We found out what happens. Offset equals 0, double space, air assist, which we'll shorten to AA, equals 3, double space, table, and we'll put the spacer after it, 12mm, table 12, double space, and then we have dimensional error, dim, equals 0.15. And of course the final thing that's missing from here is FL equals 2 inches. Save. So now we go and open up this parameter library, or the parameter layer, and we'll find all the dimensions in here. Let's change this one, for example, to 2. They're all rubbish parameters. So we go to our parameter library and we open up MDF 3mm. Click. We get all our information, additional notes across the bottom there, and all our information about the parameters here. So what we need to do is press load, and those will automatically get transferred back into here. Now I've put the wrong dimensions in here purposely, because what I want to do now is to show you how to edit things if you need to. So we really want those to be 67 and 67. After we've corrected the parameters, we need to select the parameter library and we need to do a save as. And we need to save it as exactly what this file name is here. But, and here is the but, if you do just this, what I'm going to do, and I'm not going to do it, if I say MDF space 3mm, where have all my notes gone? They're not there. So what you'll do, you'll wipe out the parameters that you've laboriously spent time putting into your library. So you cannot edit the library in this, what would appear to be a fairly simple and logical way. Cancel. Cancel. We've got to go back to the parameter library, and you'll notice that once we've opened the parameter library with a known program, it'll continue to keep opening for us. So what we've now got to do is to find out where our problem was, and the problem was here in our max and min speed, and we need those edited to 67 and 67. And now we can save it, and when we open up our library now, parameter library, MDF 3mm, load, all our parameters are still there, including our notes, and we can load those parameters into here, 24, 67, 67. Job done. Okay. I'm sorry that's a bit of a drag. I've had to purposely make mistakes to try and reinforce to you how this system works. It is not logical and straightforward. Well, you may remember when I was decrying the credibility of existing parameter files that I said to you, I haven't got a whole list of these files because I'm too damn lazy. You can see what a tedious, laborious process it is. But
you can also see, hopefully now, that it is a very necessary process to gain understanding of materials and various aspects of your machine. I can accept that what we've just been watching for the last hour has been very, very, very boring. Hopefully when you get to do it, you'll find it slightly more exciting, because if you get it wrong, your job will be wrong. Well, I suppose it could be likened to somebody asking you to knit a parachute and then make you wear it and jump out the plane to see whether it works. I've changed the picture on the screen because this is what you might see. I'll leave you with that thought, and I'll see you next time.